For our second objective, we're continuing with our volume focus. This time it's going to be a little bit different. We're finding volumes of solids that have a known cross-section. Now you can make a case for the previous objective having known cross-sections of being, say, little cylinders. They're disks, they're washers, but we're going to generalize it so that those cross-sections can be any kind of similar shape. If you take a look at the image here, this is a photograph of the Kauffman Center for the Performing Arts in Kansas City, and very interesting building. You can see that you have basically two parts to it. You have this kind of shell that is closest to us. There is an acoustically sound performance center here, and then there is a separate one down there in the background. Very cool building, and sort of looks like somebody's calculus project. Sort of looks like, I don't know, something like this. So here we have a three-dimensional shape, and we're going to take some slices of it, some cross-sectional slices, and those slices in this case sort of look like slices of bread. On the AP Calculus exam, our cross-sectional slices are most commonly squares. That's probably number one. And then we have rectangles. We could possibly have triangles. Triangles, I'm thinking equilateral triangles or isosceles right triangles. You know, those 45, 45, 90 triangles, very, very common. We have trapezoids, and then probably number two in line are semicircular cross sections. So here's kind of the gist of it. We're going to break up our three-dimensional shape into slices by partitioning our interval here, and then all of those cross-sectional slices have a similar cross-sectional shape. We're going to find the volume of one of those cross-sectional shapes and then just add them all up. I think we can do that with a definite integral, right? Okay, so to begin this process, let's take a look at this new shape. So for this three-dimensional shape, its base is basically a circle. You can think of it as two square root functions, the one for the top and the one from the bottom. The distance between two corresponding points on those two functions, that's going to become the base of our cross-sectional equilateral triangle for this particular one. And again, whatever shape that we use, we can use triangles, we can use squares, we can use semicircles. We're going to see some images of that coming up. All right, so if I wanted to find the volume of this shape, realize that this actually is going to make a very, very skinny triangular prism, right? Because it's going to have a little bit of width. That width is going to be our delta x here, whatever our partition is. So how do I find the volume of a prism? I find the area of its base, which is going to be the area of our cross-sectional region, and then we multiply it times our delta x, the width. So we find the area of our cross-section, and we multiply it times the width. That gives us the area of one cross-sectional piece. We want to add up maybe n of those things. We'll do that with a Riemann sum. So let's take a look here. So we have the summation from I equals 1 to n. This is the area of one of the cross-sectional pieces multiplied times its width. It is a Riemann sum because you get a function multiplied times the width. So here we can see some images with the exact same circular base, but with different cross-sectional pieces. Here we have squares. So you can see the distance between those two corresponding points on the circle. That becomes the side length of the square. All right, and then here's the equilateral triangle one that we were just talking about. This time, the distance between those 2 points becomes the diameter of a semicircle, or maybe it's an isosceles right triangle. It becomes the hypotenuse of the isosceles right triangle. That's pretty common, or sometimes they do one of the legs of the isosceles right triangle. All right, back over here to this Riemann sum. It's just an approximation of the volume. How can I get the exact volume? Well, we know what to do. We take the limit as n approaches infinity here, which is going to turn that, of course, into a definite integral. And so please write something down. Here is our general volume formula. It takes the definite integral over our interval from a to b of the area of our cross-section with respect to x. The reason why this is a general formula for volume, because the one for the disk method and the washer method is basically this one in disguise, as special cases of it. So let's think of the one for the disk method. We took pi r squared and multiplied it times dx, right? Dx being sort of the height of our little cylinders. Well, pi r squared just basically means that you have circular cross sections, and that's the area of our cross-sectional piece that's right here. Let's take a look at some models sort of to understand the difference between these two methods here. So I'm going to switch to the camera view. And imagine, if you will, that this was a set of functions that was graphed in the coordinate plane. So we have something that is parabolic, and then we have a line down here that intersects it. It's kind of stair-stepped here because you're going to see that this forms the base of a solid, or this is the shape that's going to get revolved around a particular axis. Okay, so speaking of that, let's rewind back to our first objective and when we were talking about a solid of revolution. So this would be, say, this is the x-axis that's right here. Imagine it, if you will. And this being in the coordinate plane, we're going to rotate this thing around 360 degrees to create a solid. And basically the distance from the x-axis to our function in each one of these cases is going to make the radius of that circular disk. Okay, so here is an image of what that looks like. Not an image, an actual model. All right, so it's hard to see from this that that's exactly what that shape was, but if I turn this thing upside down, you can see that here is that parabolic shape, and then here's the line. Of course, this is shrunk down quite a bit to save some sort of materials, and it's not the whole entire 360-degree rotation, again, because it was super expensive to actually print this out, 3D print this. One of my students did this as part of their project, and it's fantastic. Again, so you can see here that the distance, this would be the axis, the x-axis. Distance from here up forms the radius of that larger that larger disk. Okay, these are actually washers, of course, especially as we get a little bit further, because now we have this hole that we're taking out, and this hole in this particular case would be like a conical cutout right there. Okay, and again, imagine that there were two halves of this that would be crammed together. This is a solid of revolution, but you can make a case that it has similar cross sections, right? And those cross sectional shapes are just circles. All right, now let's go back to this base shape here of the parabola, which is intersected by the line here. Okay, and now this time we're going to say the distance between the two functions. So that's going to be the line and the parabola. The distance between these two functions here, that's going to become, it could be the diameter of a semicircle. It could be the side length of a square that's going to come out at us. It could be the hypotenuse of, let's say, a right triangle. Again, that's going to come up and on another axis. So the one that I have here is this exact shape. So it fits on there very nicely there, right? Which has semicircular cross sections. So again, the distance between the two functions becomes the diameter of this semicircle. If I flip this around, you can see a mirror image of that parabola shape and then the line that intersects it. And we have a whole bunch of these semicircles. It sort of looks like that Kaufman Center, right? That's why I'm saying it. It looked like somebody's calculus project. They became an architect as a result of it. All right, and the distance between those two shapes, that's the diameter of each one of these cross-sectional shapes.